Hi everyone, so here we are on the very last section of chapter 20, and this is going over the differences between strong and weak acids and bases. So here I have a few different terms: concentrated, dilute, strong, and weak. So these are some terms that we're going to come across in this last section, and you need to know the differences between them. Just because a solution might be concentrated, it has no relation to the strength of the acid. Okay, and that's what we're going to go over first. So these terms right here, strong and dilute, refer to the concentration or the molarity of a solution. Concentration, okay, or the molarity of the solution. When we are talking about the, how much solute there is compared to solvent, then obviously we would classify it as being concentrated if it has a lot of solute and a very little solvent, and then dilute is the opposite, has a lot of solvent and then very little solute. Then the terms over here, strong and weak, mean something completely different, okay? So strong and weak have no relationship to the concentration of the solution. Strong and weak depend on what we call the ionization of the acid or base in solution. Okay, so then let's see how I want to word that. So strong and weak refer to how much, that's an M, how much the acid or base dissociates in solution. Okay, SOLN is my abbreviation for solution. So how much the acid or base dissociates in solution. In other words, how much it separates into ions. Okay, that is what strong and weak is referring to. How much it will separate into ions when it is dissolved in water. All right, so when we fill in these blanks here, these are intended to be like you can make a blank acid dilute. So you can make a strong acid dilute, okay, but you cannot make a weak acid strong, okay, and that's what those are intended to be. And so what this is saying, it's saying that, yeah, just because you have a strong acid, it doesn't relate to the concentration at all. You can dilute it, or it can also be very concentrated. But if you have a weak acid, it can never be converted into a strong acid, okay? And vice versa. If you have a strong acid, it's never going to be classified as a weak acid. So they have no relationship to the terms concentrated and dilute. That is all just relating to the concentration of the solution. All right, so the first thing we're going to talk about further are strong acids. So notice here, strong acids totally ionized in solution. That means they completely separate into ions. 100%. They will separate into ions when they are dissolved in water. So since they completely separate into ions, we classify strong acids as being strong electrolytes. So remember, once again, electrolytes are solutions that conduct electricity, okay? These are your 5 strong acids that need to be memorized, okay? So memorize these. There are more strong acids than the ones that I have listed here, but these are the ones that I want you to be responsible for this class. So they're not that hard to memorize. So HCl, HBr, HI, well, Cr, Br, and I are all found in the halogen group. Then you have 2 of them that contain polyatomic ions, okay? Nitric acid and sulfuric acid. All right, so memorize those as being strong, and then everything else, all the other acids you come across, you are going to assume is a weak acid. So something that we have written here, look at this equation. So HCl, which is one of your strong acids, notice here we use a single-headed arrow. That is really important. If it's a strong acid or a strong base, we use a single-headed arrow, and that represents that it separates into ions 100%, into H plus and Cl minus. Okay? Now another way you can write this, you don't have to add water to your equation, but if you do choose to add water in your equation, you will still use a single-headed arrow, but instead of H plus, you are going to get hydronium, H3O plus, and then the chloride ion in solution. Okay, remember I had talked about before that H plus and H3O plus are equivalent to each other. They are the same thing. So it doesn't really matter if you add water to the equation or if you choose not to add water. Okay, but if you do choose to add water to your equation, then you have to make hydronium on the product side. All right. Okay, so those are strong acids. Now, I don't really have a separate slide on strong bases, so then let's just add strong base information to your notes. But the concept is still the same. For a strong base, it will still have a single-headed arrow, okay? But on the next slide, let's write down all of the strong bases or how you identify if something is a strong base. So let's do this in blue because bases are blue. All right, so strong base. All right, so this is how you identify the strong bases. It's when you have, sorry, that keeps marking down there. It's when you have hydroxide, which is OH minus, combined with a metal from group 1 or 2. So those are your alkali metals and your alkaline metals, except for magnesium. Okay, so you need to add that to your notes. So once again, the strong bases are where you have hydroxide combined with the metal from group 1 or 2 except for magnesium. So you have to be able to recognize your strong bases. Don't forget NH3, which is ammonia. It does not have hydroxide in its formula, but this is a weak base. Okay, so that is the base information. But also, just like your strong acids, the strong bases will be strong electrolytes also, since they do separate 100% into ions. All right, so here we have a picture here, a bar graph going over the differences between a strong acid and a weak acid. So this top picture, so let's take a look. This bar graph here. So this is before it dissociates in water, HA, which represents a generic acid. Now notice what happens after the dissociation in equilibrium. So it says that, according to the bar graph here, notice the height of the bar graph. They are all the same. So this is representing a strong acid, showing you that it completely separates into ions 100%. So notice here, I drew a single-headed arrow to represent that. Okay? So this, let's write, this is strong. Oops, strong. Okay, and then let's take a look at the bar graph on the bottom. So here's your acid, but look what happens. Most of it still stays together as the acid, and then it only separates into ions to a very, very small extent. And this is an example of a weak acid. So if it's a weak acid, we do not use a single-headed arrow. If it is a weak acid, we actually use a double-headed arrow. Okay? So the double-headed arrow here represents that most of it is going to stay together. Okay? And only a small percentage, like usually around 1% or less than 1%, will actually separate into ions. Okay? So that's what the double-headed arrow represents. It does not separate into ions very much. Most of it stays together. Okay? And that is a weak acid. All right, so that means that your weak acids, they don't separate into ions when they are dissolved in water very much at all. It happens to a very small extent. But they do separate into charged particles, therefore they are still electrolytes. Okay, they are still electrolytes, but they are poor electrolytes, meaning that they're not going to conduct a lot of electricity, but they will conduct some. It's kind of like the Gatorade, when we tested the Gatorade with the light bulb and everything, how it was very, very dim. So that's what a weak acid would do. And then your weak acids are basically anything that was not mentioned from those 5 that you had to memorize. And then everything else you are going to assume is a weak acid. So here we have a weak acid. Notice this is the polyatomic ion acetate, if you did not recognize that. So this is called acetic acid. It's not one of the 5 acids that you had to memorize, so we use a double-headed arrow, and then we still show the dissociation of the acid. It does separate into ions, but it only separates to a very small extent, so we represent that by using a double-headed arrow. And that is the same idea also for weak bases. So I don't have a separate slide for weak bases, but that's the same idea. Double-headed arrow for a weak base, okay, poor electrolyte, only separates to a very small extent. So since we have a double-headed arrow for your weak acids, then that means we can have equilibrium, all right? So that is where we get this value or variable here, Ka. So the capital K for the equilibrium constant and then a little a for acid. And if we were doing this for a weak base, instead of Ka, we would use Kb, B for base. And so if we had the reaction of HX, let's just say this is some type of generic weak acid, we would use a double-headed arrow. Okay, we would still show what it would look like if it were to dissolve in water. Okay, so it separates into its ions like that. So notice here, when we write out the Ka expression or the equilibrium expression, it is still products over reactants. Okay, that's an R. Products over reactants. So products on top. Okay, don't forget the coefficient would become the exponent. Okay, so products on top and then the reactant on the bottom. All right, and then numbers would be provided, and we'll do some math with this also, and we'll do this on the worksheet when we get there. All right, now it is also important to know that just because it's a weak acid, it doesn't necessarily mean that all the weak acids are equal in strength. There are some weak acids that will separate more into ions than others, okay? And so there might be some stronger weak acids, but it's still classified as a weak acid. And to compare your weak acids, we look at their Ka values, okay? We look at their Ka values. So it states right here, the larger the Ka, the stronger the weak acid, okay? So we can, once again, put these acids in order of strength by looking at their Ka values. Once again, the larger the Ka, the stronger the acid, okay? And that would go also for Kb, for base. The larger the Kb, the stronger the base is going to be. That just is telling us that it's breaking up more into ions. All right, so this is the very last picture. Once again, trying to emphasize the difference between what is a strong acid and a weak acid. Okay, so take a look at these 2 beakers and think about our definitions for a strong acid and a weak acid and see if you can figure out which one is which. Okay, one of them is a strong acid, one of them is a weak acid. All right, so this one on the left here. Okay, you can see all of the ions and what they represent. So which one do you think would represent a strong acid? So remember, a strong acid will completely separate into ions 100%. So your strong acid would be this one right here, right? So let's write strong acid. You can see how all of these molecules, or I should say ions here, all of these ions, right, they're completely separated and floating around into solution. Therefore, the one on the right, this is a weak acid. Remember, weak acids do not separate very much at all into ions. And you can see that it was only this one right here that actually separated, and then everything else, notice, stayed together. Okay? So that is the difference between a strong acid and a weak acid. So what we're going to do now, we'll do this, well, we're not going to do it now, but we're going to do it in class. We're going to go over the 20.4 worksheet, and now we're going to apply all of these concepts and go over the math that relates to this. All right? And that is about it. So I will see you guys later. Bye.